Hello my Chinas, Big Mike here, and today I wanted to talk to you about evolution and some of the problems that I had with evolution when I was learning about it, and maybe expose you guys to these problems that I had to help you think outside the box. I'm going to start with a 3D animation from the DNA Learning Center. If you want to watch this video at a later time, I will include the link in the description below. And what this video is describing is the process of transcription.
What you are about to see is DNA's most extraordinary secret: how a simple code is turned into flesh and blood. It begins with a bundle of factors assembling at the start of a gene. A gene is simply a length of DNA instructions stretching away to the left. The assembled factors trigger the first phase of the process, reading off the information that will be needed to make the protein. Everything is ready to roll. 3, 2, 1, go. The blue molecule racing along the DNA is reading the gene. It's unzipping the double helix and copying one of the two strands. The yellow chain snaking out of the top is a copy of the genetic message, and it's made of a close chemical cousin of DNA, called RNA. The building blocks to make the RNA enter through an intake hole. They are matched to the DNA, letter by letter, to copy the A's, C's, T's, and G's of the gene. The only difference is that in the RNA copy, the letter T is replaced with a closely related building block known as U. You are watching this process called transcription in real time. It's happening right now in almost every cell in your body.
Alright, so the process of transcription. This yellow chain that is made here, they didn't say it, but it is a molecule of mRNA. And this mRNA then combines with rRNA, also known as a ribosome. And what that will then do is use other building blocks to form a similar chain, which will then be made into a protein. And that process is called translation. And there are millions and millions of proteins in every cell. And just think about how complicated this is. This is going on along each DNA strand. There are millions of genes and just millions of proteins going on. So one thing I wanted to also point out is, if you paid attention in that video, to the language the woman was using. She was using words such as information, instructions, reading, copying, code. So let's take a look at just the definition of the word code. A system of words, letters, figures, or other symbols substituted for other words, letters, etc., especially for the purpose of secrecy. And in computing, it's used for program instructions. Let's look at the definition of transcript. Transcript is basically the mRNA, this yellow chain. A written or printed version of material originally presented in another medium. Well, here we go, a length of RNA or DNA. But basically, an official record of student work. Let's see what the definition of translate is, which is the process of translation. Express the sense in words or text in another language. So basically, you can see why the developers of this gene theory use these words because they understand DNA to be a language. Okay, you can't just copy and translate and write and proofread. You know, we have proteins that do all these functions, and we understand DNA to be a language, and a language comes from an intelligence source. It doesn't come from randomness. I mean, if I just take this here and copy, you know, and paste it somewhere else, then that is very efficient. But if I take a million monkeys and have them type on a million typewriters, I wonder how long it's going to take them just to, you know, type these two words out. Statistically, it will never happen. All right. So you see, another thing I wanted to point out about these transcription factors is they themselves are proteins. You see, it says the transcription factor is a protein. So what does that mean? That means that there is a gene in the DNA that has to be read and translated and transcripted before this protein can be made. Interesting, isn't it? So these proteins that are reading and you know, producing mRNA, they have to produce the mRNA to produce themselves, and that is in this code. So this is now we're getting into one of the problems I have. But before we get into that, let's just see, because you know, evolutionists love this thing about, you know, how does it come along, how do we have the change in species, etc., and it comes along by mutations. So let's see what happens if we have a mutation in these transcription factors. Do we expect that, you know, through mutations these transcription factors kind of evolved in different species, and you know, what happens when we have mutations? Do we get something better or something worse? Well, here we have a few examples of what happens when you have a problem in your transcription factor. Rett syndrome. Mutations in the MECP2 transcription factor causes Rett syndrome, a neurodevelopmental disorder. Diabetes, a rare form of diabetes called MODY. Maturity onset. Okay, so this is like people with type 2 diabetes that get them when they're 12 years old. Here we go. Another mutation in the transcription factor. Developmental verbal dyspraxia. Mutations in the FOXP2 transcription factor. Autoimmune diseases. Mutations in the FOXP3 transcription factor. Li-Fraumeni syndrome. Tumor suppressor P53. Breast cancer. Multiple cancers. So my point is that if you have mutations, we should have another table here saying a mutation in this transcription factor makes you stronger, gives you bigger muscles, instead of cancer. Do you guys see what I'm saying? But we don't have a table like that. The only table that we have is what mutations actually cause. Anyway, that's just a side note. I wanted to get into, you know, the first cell and the theory of where this first cell came from and the origins. So basically, the first cell is theorized to be something like this. You have this biphospholipid membrane, and then you also have just an RNA strand in there. And the reason why scientists think it's an RNA strand is because we have this RNA world theory where in the early developmental stages of life, what we had was just the different forms of RNA. So tRNA is the building blocks of proteins, and mRNA is the messenger RNA that is translated from the DNA. So, you know, the fallacy that I see here is you have the DNA, which can be thought of as a book. The transcription factors can be thought of as a copying machine. The mRNA can be thought of like a copy of one page out of the book. And then the ribosome or rRNA can be thought of as reading that page and making a machine, or whatever, making something from those instructions. But it can only read the copy, and it can't read the book. It can just read that one page. That's like the simplest way I can describe it to you. So basically what they're saying is that over millions and millions and millions of years, what you had was these mRNAs coming into existence and then somehow kind of being reverse engineered into the book or the DNA. How this process could have come about just boggles my mind, because just like the example I gave you earlier, if you just take one sentence and take a million monkeys and have them type on keyboards, what are the chances that they're going to come up with just that one sentence? Now we're talking about for a gene, for one protein, we're talking about a very complex, and it has to be a very specific code, because like I showed you, if you have just one mutation, it doesn't work. Okay, so just something for you guys to think about. I'll probably be making some more videos about evolution. Okay guys, have a good day.